Okay, our fourth of the 5 sessions is improving the performance of web streaming by super resolution upscaling by Navajit Borman. Thank you.
Thanks, Will. Hello, everyone. I am Navjit, and I will be presenting our work together with Yuri and Patrick on improving the performance of web streaming by super resolution upsampling. Before moving into the topic, I would like to set the context and define some objectives of this talk. So traditionally, video scaling in web browsers have been limited to classical signal processing techniques, such as we have bicubic interpolation. Before that, we had bilinear. Or you can use filters such as sync or lens course and all, which are a bit more complex. Recently, we have seen a relatively new trend of AI-powered scaling, which is also called as super resolution. And some of these approaches have shown to be outperforming the traditional approaches, right? But the introduction of this new paradigm brings with itself a set of questions that needs to be answered before it can be adopted into the mainstream ecosystem of video streaming. For example, what are the advantages of traditional of SR over traditional upscaling? How can we model or quantify super resolution scaling capability? So that's a very important question that we need to answer. How we can use SR for improved image or video delivery, since we have this capability now, how can we use that in our ecosystem? And most importantly, the question arises is, how significant gains are we talking about here, right? So if we are using super resolution compared to bicubic in traditional ABR streaming this one applications, what are the gain percentage we are talking about here? So this talk will try to answer some of these questions above, bring some relevant results, and the idea of this talk is also to encourage discussion among all the participants here. So again, this is not, how do I say, quite far away, distant in the future. So there has been increasing support of video super resolution in browsers. So recently, there has been support in Microsoft Edge and Chrome, and vendors such as Intel, AMD, and NVIDIA are increasingly supporting it. And it has been used and shown to outperform traditional algorithms from traditional videos that we have, right? Say movies, animation, and all. And also in gaming, right? So this is one of the most, I would say, popular applications of super resolution. Importantly, because gaming PCs and all, they already have good GPUs and all. So you can use this kind of technologies in the background to upscale it to very good quality. And we have seen in the talk earlier today in the morning, and there are a lot of proprietary solutions because of the advantages offered by such upscaling algorithms, AI-based upscaling. We can see here that we have, I don't know if, we have, for example, BitClear solution from iSize. We have solutions from Espresso Media, from a new startup from Korea. And we saw the presentation from MediaKind where they are proposing Atlas upscale, so their own proprietary solutions. There have been a lot of research work ongoing, so it's almost here. So we have work such as anti-IRE workshop, where there is work on improving the algorithms, and not only limited to 2D videos, right? So we have super resolution coming to 360-degree videos, light field, you name it, and it's almost there. And we have low complexity algorithms also, so focusing more on the mobile application side. So now that we have seen the advantages of such algorithms, so we need a model to quantify such capability, right? So for that, we need to understand the impacts of scaling on perceived quality before we go into modeling that. And for that, what is very important is two angular metrics. So one is the viewing angle, so which is shown here by phi, which is nothing but the angular span of capturing the size of the video that is projected on the screen, right? So we have a video here of W cross H pixels, which is upscaled to fit the display or the player size of WB cross HP, and then we have the phi. And then we have angular resolution, which is the Nyquist frequency of the video that was encoded and delivered. Again, the formulas are mentioned here, and it's also in the paper, so you can have a look. A very well-known model, which is of relevance to our context, is the Westeringer-Roof model. It's the best-known model that predicts the perceived quality directly based on the picture resolution. So it's a very classical model, like proposed more than 30 years ago. So what happens is that based on a series of psychophysical experiments, what they observed is that the perceived quality grows approximately as logarithm of viewing angle, and then it also grows with angular resolution, but then it starts to saturate around 25 to 40 cycles per degree. And they provided a model which can, based on these two parameters, you can try to predict the quality of the picture that was displayed on the screen, right? However, and we actually did refit this model to many modern data sets. So the reference is provided at the end. So, and we saw that this model actually performs quite well to variety of different devices and viewing setups. So it's not outdated, actually. But there is one limitation of this model, that it doesn't have any parameter which will allow us to take into account the upscaling algorithm or also differences in content, because it was designed quite a long time ago. So we don't have any parameter to allow us to take into account differences between HDR or SDR content and also the upscaling algorithm. So last year in QMX, we presented a work which actually is a generalized version of this model, which again, we have introduced some parameters here to allow us to take into account differences in upsampling algorithm. And if you see the fit here on different devices with different viewing angles and encoded resolutions, it actually performs quite well. And it kind of, by a small margin, does outperform the traditional model. Like I said, most importantly, the proposed generalized Westering roof model here, it provides us with two parameters that allow us to take into variation the perceived quality due to differences in upscaling algorithm, which is here mu s, which is the saturation value of angular resolution, and the L parameter controlling the slope, right? And what we did is then we fit this new model, the generalized Westering roof model, to the Bristol Vision Institute dataset. So this is one of the few datasets which have quality scores. It's MOS scores for different upscaling algorithms, including one super resolution. So what you can see here is that in the blue line, we have the fit to the super resolution, and with the bicubic fit, right? So the traditional classical signal processing technique. So what we observed here is that the use of SR actually lowers the saturation value of mu s while increasing the slope parameter. So the values are provided in the paper. You can have a look. So now we have actually a model, and how can we now use this model to improve the delivery of, say, video and images over typical ABR, streaming application? And how significant gains are we talking about? So going back again to the basics of resolution selection in ABR streaming, as we know, earlier it was limited mostly to so network bandwidth, right? You check the network bandwidth, and then you have maybe bitrate throughput-based model or hybrid, taking into account, say, buffer or these kind of parameters, and you adapt your resolution to that. But in streaming, so modern web-based streaming clients, you are usually typically resizing the player size to different, as per your convenience. So you have web pages where the player gets resized and all. And then many streaming clients actually use adaptation to player or window size, which makes sense, again, because you don't want to pull a 1080p rendition for a 360p player size, right? So, but what happens is that in most of these cases, the adaptation logic is very simple. So there is a limit on the upscale factor, or you just select the nearest matching rendition resolution. So these algorithms are not device, how do I say, device size aware. So these are device size aware, but not like device aware, because you are not taking into account if it's a mobile device or it's a TV or it's a tablet or PC, right? So you don't have this, no parameters controlling the selection of algorithm, the resolution for the streaming. And what we know for sure is that in all these cases, no one takes into account the upscaling algorithm that is being used at the client end. But things can be done better, and this is what we actually had presented last year. So we presented an algorithm which actually is device aware now. So what we have here is, for example, we take into account the viewing angle and angular resolution for the different viewing setups, and then we select the best resolution, considering the MOS as computed by using the generalized Westering roof model that we proposed. And what we found is that actually the selection of rendition, optimal rendition selection behavior is quite different for different devices. We have here examples of 47-inch HDTV, we have PC, mobile and tablet. The selected resolution for different player heights, if you see here, are actually quite different for all these devices. So what we did in this work is actually we go one step ahead. Now what we are trying to do is we are now going a step ahead, not only taking into account the device characteristics, right? So we are also taking into account the upsampling algorithm that is used in the device. So for that, what we did was we actually proposed two modified algorithms. What you see on the left-hand side is an algorithm which selects the optimal rendition considering bicubic upscaling, right? So we are using here the mu, s, and l parameters based on the fitted value that we get for the bicubic scaling. And what the algorithm 2 does, again, this is for the simulation purpose, right, to understand the benefits of using super resolution. What we try to do here is that we have a modified algorithm again, and here we are assuming that the client is using super resolution upscaling, but we try to match the quality that would be achieved by bicubic scaling while selecting a possibly lower rendition. So that's the basic algorithm. These two algorithms, what they do, actually. Again, going back, so now we want to see how these algorithms perform. So what we did was we considered the typical ladder of resolutions as proposed in DVB-Blue Book 168. So we have up to 4K, starting from 192 cross 108 pixels to 4K resolution, right? And we encoded one of the sample videos, so at different, again, resolutions and bit rates. So these bit rates are optimized for the content using our proprietary solution, context-aware encoding solution. And now if we go into the plots here, so what I show here is again, this is for one of the TV screens. So considering a TV screen, what we see here on the x-axis is the player height. So if we are varying the player height across whatever possible range we have, and on the y-axis, we have the rendition selected. What we see here is that in the green is this rendition selected for bicubic upscaling, right? And in the blue, what we have is for the super resolution. We see that super resolution-based upsampling actually enables much more conservative choices of rendition than that of bicubic. In this example, we see, for example, 16% reduction in frame height or 30% in pixel count in the high-resolution regime here. Looking at the bitrate player height curve, so on the y-axis, we have bitrate in kilobits per second. What we see here is, again, especially when we are considering playback at the higher resolution domain, right? What we see here is that super resolution-based upsampling actually selects renditions which are much lower bitrate than compared to bicubic. In this particular example, again, we have a savings of up to 38.9% bitrate, right? So that's quite significant. Again, this is considering the whole range that you're using, the whole range of this, and it will vary depending on what resolutions your clients are playing the videos and all. But for this specific case, we see quite a good bitrate saving, and that means significant reduction of network bandwidth usage. And if we just look at the MOS versus bitrate curve, again, we see that super resolution definitely outperforms the bicubic upscaling, and even at lower resolutions, lower bitrate. So like I said at the start of this talk, this is not to force some ideas on you. It's just to start a discussion in the community. What we see based on this work is that super resolution techniques definitely shows clear promise. The performance is getting better. Not all of the super resolution model actually outperforms even bicubic. If you see the different comparison charts from academic papers or from MSU super resolution, you will see that there are actually models who might perform worse, but there are quite a few recent models, real basic VSSR and all, which actually performs quite well compared to the bicubic upsampling, or even Landscope for that matter. But however, to start this, using these techniques, we need clear defined APIs supported by browsers and platforms, and we need methods to quantify the effects. So we presented one of the approaches where we showed how we can use the generalized model that we proposed and adapt it to different upsampling algorithms. That need not be the only way. So there can be different models. There can be different approaches of doing that. Some possible steps forward is what we need to do as a community is to standardize APIs, again, at browser and possibly OS levels. We had discussions during the panel. Going alone is probably not the best idea, so it will probably to scatter results and all. Standardize possibly the implementation of SR algorithms, again, similar to codecs and all. But again, there are different pros and cons, which we, as the industry as a whole, need to decide on. And also define quality models, right, to quantify their models' performance. For example, It is well known that VSNR and SSM and all, they don't usually perform that well for super resolution-based upscaling. So they rely on something like LPIPs or maybe subjective measures. So again, a lot of challenges and opportunities for the industry. With this, I conclude my talk. If you are interested in discussing more, connect with me on LinkedIn, and I'm happy to answer any questions if we have time.
The count is 0, but everyone gets a question as long as it's a quick one. Yes, you take the mic, please.
Hi, thanks for the presentation. It's obviously a topic that I'm very close to. Can you specify what you used for as a super resolution reference?
Yeah. So this is the citation is here. Is I don't remember the short form. So it's the paper from one of the highly cited paper from Kim from 2016. And we kind of had to use this model because that's what was used in the data set, right? So we are kind of restricted by the choice of super resolution algorithm. Again, here we are not, how do I say, advocating any particular super resolution algorithm, and that's not our purpose. It's to show the benefits. So again, the values shown here will vary depending on the implementation, usage of what percentage of players are of which size and all. So yeah.
Yeah, because.
But the citation is here, so it says. It's not visible. Okay. It's in the paper, so it uses the super resolution algorithm from Kim and all from CVPR 2016.
Yeah, okay, so it's, well, just to point out, I mean, it's a very fast-moving area of research. There's hundreds of papers.
So yeah, it's quite an old model. Like I said, there are many new works, real basic VSR, VSR++. There is comma ISR from Google and all, so there are a lot of models.
Yeah.
But yeah.
But I mean, this only makes your model even more relevant.
Relevant,
right?
yeah,
Because
exactly.
Well, the super resolution performance increases, so will the difference between the bicubic.
Yeah, so this will, probably the results will be even more promising, yeah.
Right, thank you very much. Another round for Nabajit, please.